Download this code from codegive.com, link in the description below. Buffer Overflow Attack Tutorial, diving deep with code examples. This tutorial will guide you through the concept of buffer overflow attacks, explain how they work, demonstrate a simple example, and discuss mitigation techniques. We'll focus on the core concepts and common scenarios relevant to the OWASP Top 10 and secure coding practices. Disclaimer *: This information is for educational purposes only. Attempting to exploit vulnerabilities on systems without explicit permission is illegal and unethical. Use this knowledge to understand and prevent vulnerabilities, not to create them. 1. What is a buffer overflow? A buffer overflow is a programming error that occurs when a program attempts to write data beyond the allocated memory boundary of a buffer. A buffer is a contiguous block of memory allocated to hold a specific type of data. When more data than the buffer's capacity is written into it, the excess data overwrites adjacent memory locations. Why is this bad? This seemingly simple mistake can have serious consequences. Corruption of data. Data stored in adjacent memory locations can be overwritten, leading to unpredictable program behavior or incorrect calculations. Program crash. Overwriting critical program data, like return addresses or function pointers, can cause the program to crash. Code execution. A malicious attacker can carefully craft the overflowing data to overwrite the return address of a function, redirecting the program's execution flow to injected code. This is the most dangerous form of buffer overflow, allowing arbitrary code execution with the privileges of the vulnerable program. Denial of service. DOS. By intentionally overflowing a buffer, an attacker can cause the program to crash repeatedly, making it unavailable to legitimate users. 2. How does a buffer overflow happen? The root cause of buffer overflows is the lack of proper bounds checking in the code. When a program reads data from an external source, like user input, a file, or a network socket, and copies it into a buffer, it must verify that the size of the data doesn't exceed the buffer's capacity. Common scenarios that lead to buffer overflows. strcpy, function the strcpy, function, and similar functions like gets, copies a string from one location to another without checking the size of the source string. If the source string is larger than the destination buffer, a buffer overflow will occur. This is perhaps the most classic source of buffer overflows. Sprintf, function the sprintf, function formats data and writes it into a string buffer. If the formatted data is larger than the buffer, an overflow will occur. Looping constructs without bounds checking. Loops that iterate over data and write it into a buffer can be vulnerable if the loop doesn't verify that the number of iterations doesn't exceed the buffer's capacity. Off by one errors. Sometimes, the bounds check is present, but it's implemented incorrectly. For example, allocating a buffer of size n and then iterating from 0 to n, inclusive, is an off by one error that can lead to a buffer overflow. Integer overflow. Integer overflows can lead to buffer overflows indirectly. If a program calculates the required buffer size using an integer calculation that overflows, it may allocate a smaller buffer than needed, leading to an overflow when data is written into it. 3. A simple buffer overflow example, C. Let's look at a basic C code example that demonstrates a buffer overflow vulnerability. Explanation *. 1 char buffer 10, *. This declares a character array named buffer with a size of 10 bytes. This is where our overflow will occur. 2 char input 100, *. This declares a character array named input with a size of 100 bytes. This is where we'll store the user's input. 3 gets, input, size of, input, stin, asterisk the fgets, function is used to safely read input from the standard input, stin. It takes 3 arguments. Asterisk the buffer to store the input, asterisk the maximum number of characters to read, including the null terminator. We use size of, input, to specify the size of the input buffer, preventing a buffer overflow in the input buffer itself. Asterisk the input stream, stin. For strcpy, buffer, input, asterisk this is the critical and vulnerable line. The strcpy function copies the contents of the input buffer into the buffer without checking the size of the input. If the user enters more than 9 characters, plus the null terminator, the strcpy function will write beyond the bounds of the buffer array, causing a buffer overflow. 5 printf, you entered, %s\n, buffer, asterisk this line prints the contents of the buffer array to the console. After a buffer overflow, the output may be unpredictable. How to compile and run, on Linux with GCC. 1. Save the code save the code as overflow.c. 2. Compile the code, without security features. No stack protector, disables the stack protector, a security feature that detects buffer overflows. We disable it to make the vulnerability easier to exploit for demonstration purposes. Never disable stack protection in production code. Z exec stack, allows code execution on the stack. Modern systems usually prevent this by default. We need this for a simple exploit to work. Never allow stack execution in production code. No pi, disables position independent executable. This makes the address space predictable, also useful for exploitation. Never disable pi in production code. 3. Run the code Experiment enter a short string, less than 10 characters, when prompted. The program should work normally. Enter a longer string, more than 10 characters. You'll likely see a crash or some other unexpected behavior. Why does it crash? When you enter a string longer than 9 characters, the strcpy function writes beyond the bounds of the buffer array. This overwrites adjacent memory locations, which can contain important program data, like the return address of the main function. When the main function returns, it tries to jump to the address that has been overwritten, leading to a segmentation fault, crash. 4. Exploitation, a basic demonstration, dangerous. This is a highly simplified demonstration of how an attacker could exploit this vulnerability. Real-world exploits are much more complex. The goal is to overwrite the return address of the main function with a different address, causing the program to jump to that address when main returns. In this example, we'll overwrite it with the address of the printf function, so instead of returning properly, the program jumps back to printf, which will likely result in another crash or unexpected behavior. For a more sophisticated exploit, the attacker would redirect execution to shellcode, malicious code injected into the buffer. Steps, very simplified. 1. Determine the offset to the return address *. You'll need to figure out how many bytes you need to write into the buffer to reach the memory location where the return address of the main function is stored. This depends on the compiler, operating system, and other factors. You typically determine this with debugging tools like GDB. Let's assume, for simplicity, that the return address is located 20 bytes after the start of buffer. This is highly simplified and unlikely to be accurate in a real scenario. 2. Craft the exploit string *. Create a string that consists of padding, enough characters to fill the buffer up to the return address. In our example, this would be 10 characters, to fill up buffer. Asterisk overwritten data for the 10 bytes after buffer. Asterisk the address of the printf function, or any other function you want to jump to. You can find the address of the printf function using debugging tools. This is highly dependent on the system and the compiled executable. We'll just make up a plausible looking address for this example, and it will definitely crash. 3. Run the program with the crafted exploit string. Use the exploit string as input to the program. Example of a crafted exploit string, illustrative, won't work directly. Let's say the address of the printf function is 0x400520, this is just an example, find the correct address on your system using GDB. The return address is located 20 bytes away from the beginning of buffer. Then the exploit string would look like this. Asterisk AAAAAAAAA fills the buffer with 10 characters. Asterisk BBBBBBBBBB fills the data beyond buffer with 10 B characters. Asterisk \x20 \x05 \x40 \x00 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 \x00. This is the address of the printf function, 0x400520 in little endian byte order, important because most x86/x64 systems are little endian. We need to express this address in the format that the CPU expects. This assumes the CPU is 64-bit. If it's 32-bit, it will be 4 bytes. The trailing zeros pad the address to the required length for a 64-bit architecture. Again, you must actually find the address and construct the string correctly for your specific system. This is where debugging tools are essential. Important notes about exploitation. Asterisk ASLR, address space layout randomization. Modern operating systems use ASLR to randomize the memory addresses of program components. This makes it more difficult for attackers to predict the address of functions or code that they want to jump to. Bypassing ASLR requires more advanced techniques. That's why we disabled pi when compiling. Stack canaries. Stack canaries are random values placed on the stack to detect buffer overflows. If a buffer overflow overwrites the stack canary, the program will detect the corruption and terminate. That's why we disabled the stack protector when compiling. Non-executable stack. Modern systems often mark the stack as non-executable, preventing attackers from directly executing code that they inject into the stack. That's why we enabled exec stack when compiling. Exploitation is complex. This is a very simplified example. Real-world exploits are significantly more complex and require a deep understanding of assembly language, operating system internals, and security vulnerabilities. They involve bypassing security mitigations like ASLR, stack canaries, and DEP, data execution prevention. Debugging is key. Debugging tools like GDB, GNU Debugger, are essential for analyzing programs, finding vulnerabilities, and crafting exploits. How to create the exploit string, Python. This Python script creates the exploit string. You would save it as exploit.py and then pipe its output to the /overflow program. Again, this won't work without modification. You'll need to 1. Find the correct printf_address using GDB or similar tools. 2. Determine the exact offset between the beginning of buffer and the return address on the stack. This will likely be different from 20. You'll need to experiment and analyze the stack layout using GDB. 3. Adjust the padding and extra underscore data variables accordingly. 5. Buffer overflow vulnerability scanning and detection. Static analysis. Tools like static application security testing, SAST, tools analyze the source code without executing it, looking for potential buffer overflows. They can identify calls to unsafe functions like strcpy and sprintf, as well as potential off-by-one errors in loops. Dynamic analysis Dynamic application security testing, DAST, tools execute the application and try to trigger buffer overflows. They use techniques like fuzzing, providing random or malformed input, to uncover vulnerabilities. Memory debugging tools tools like Valgrind can detect memory errors, including buffer overflows, at runtime. They can help identify the exact location in the code where the overflow occurs. 6. Mitigation techniques, how to prevent buffer overflows. The best way to prevent buffer overflows is to write secure code from the beginning. Here are some key mitigation techniques. Bounds checking always check the size of the data before writing it into a buffer. Verify that the size of the input data is less than or equal to the buffer's capacity. Safe string functions avoid using unsafe string functions like strcpy and sprintf. Use their safer alternatives, such as *strncpy, copies a string up to a specified number of characters, preventing overflows. However, be careful, strncpy doesn't guarantee null termination. *tinprintf formats data and writes it into a string buffer with a maximum length. *strlcpy and strlcat, safer alternatives to strcpy and strcat, available on some systems. Input validation validate all input data to ensure that it conforms to the expected format and length. This can help prevent attackers from injecting malicious data that could trigger a buffer overflow. Use memory-safe languages. Consider using memory-safe languages like Java, Python, or Rust, which provide automatic memory management and prevent buffer overflows. While still possible to have vulnerabilities in these languages, they are generally less susceptible to buffer overflows. Address space layout randomization, ASLR randomizes the memory addresses of program components, making it more difficult for attackers to predict the address of functions or code that they want to jump to. Ensure that ASLR is enabled on your system. Stack canaries Stack canaries are random values placed on the stack to detect buffer overflows. If a buffer overflow overwrites the stack canary, the program will detect the corruption and terminate. Make sure your compiler uses stack protection by default, usually enabled with the stack protector flag. Data execution prevention, DEP, also known as NXBit, prevents code execution from data pages, such as the stack and heap. This makes it more difficult for attackers to inject and execute malicious code. Ensure that DEP is enabled on your system. Compiler and operating system security features take advantage of the security features provided by your compiler and operating system. These features can help detect and prevent buffer overflows. Regular code reviews and security audits. Have your code reviewed by other developers and conduct regular security audits to identify potential vulnerabilities. Fuzzing. Use fuzzing tools to test your application with a wide range of inputs, including malformed and unexpected data, to uncover buffer overflows and other vulnerabilities. Limit buffer sizes. Don't allocate excessively large buffers if you don't need them. Use the smallest buffer size that is sufficient for the expected data. 7. Example of safe string copying, C. Here's an example of how to safely copy a string in C using strncpy. Explanation strncpy, buffer, input, size of, buffer, 1, asterisk. This line uses the strncpy function to copy the input string to the buffer string. The third argument, size of, buffer, 1, specifies the maximum number of characters to copy. We subtract 1 from the buffer size to leave space for the null terminator. This prevents the overflow. Asterisk buffer size of, buffer, 1 equals \0, asterisk. This line explicitly null terminates the buffer string. strncpy does not guarantee null termination if the source string is longer than or equal to the specified number of characters to copy. Therefore, it's crucial to manually null terminate the string to prevent potential issues when using the buffer as a C-style string. 8. OWASP and buffer overflows. Buffer overflows are a significant concern in the OWASP top 10, often contributing to A03:2021, injection *. While not directly an injection vulnerability in itself, buffer overflows often enable other injection vulnerabilities. By overflowing a buffer, an attacker might overwrite code or data that controls the execution of SQL queries or other commands, effectively injecting malicious code into the application's logic. A01:2021, broken access control *. If a buffer overflow allows an attacker to gain control of a user's session or escalate privileges, it can lead to broken access control. A04:2021, insecure design *. Frequently, buffer overflows are the result of insecure design practices, example relying on unsafe functions or failing to validate input. 9. Conclusion. Buffer overflows are a serious security vulnerability that can have devastating consequences. By understanding how they work and implementing proper mitigation techniques, you can significantly reduce the risk of these vulnerabilities in your applications. Remember that secure coding practices are essential, and you should always be vigilant in identifying and addressing potential buffer overflows. Modern compilers and operating systems offer excellent built-in protection. Make sure you are using them and not disabling them.